All right, line A6, learning task 12. We're going to go and take a look at logic gate operations. Now, you've done your pre-reading because that's what you students always do. And when you've gone through it, you probably kind of wondered what the deal was with this. It seemed like a random little bit of information to get presented here inside of third year. What are you supposed to do with it, etc. Some of you have probably made the assumption that what you're going to be asked to do is to go and deal with integrated circuits, which are going to be those little computer chips. You may have seen pictures of them before. We'll show some dual inline pin ones. They're the ones that look kind of like a centipede. They got a bunch of little legs along them, and they contain digital logic inside of them that's going to allow us to do logic gate operations. If you've got any history in this at all, that there's a whole family of logic chips, the 7400 family of chips, that is going to go and accomplish a lot of the logic that we're looking at over here. But that is not what we are about. This is a construction electrician and industrial electrician course that we're taking over here. What we're learning about these for is, yes, we could apply them to creating actual hardwired digital chips like that. But what we're actually going to be doing with this is we are going to be, in a lot of cases, doing this thing called function block language. And function block language is going to be a type of language that is utilized inside of programmable logic controllers, PLCs, as we refer to them. Function block is going to go and utilize everything that we're going to cover inside of here to go and create outputs for a system. And what we're going to do is we're going to tie a whole pile of inputs. If I were to go and take a look at my PLC, I can imagine my PLC as if it's got a whole pile of outputs over here on this side. And then on this side over here, it's going to go and have a whole pile of inputs. I'm going to go and take signals in to each of these individual inputs, and I'm going to be able to derive signals out of these other ones. It's all going to be digitally timed and things like that. This is what all of this function block stuff is supposed to go and, or not what it's supposed to be for, but that's how it's utilized these days. So we're going to focus on that end. We're going to go and talk about how we use different functions inside of it to go and combine signals. What we are going to do throughout this one is we are going to go and work at replication of a really common motor control system. I know, it's not in your books, but this is the end gate that they're shooting toward. They just don't tell you about it. I know about it, so that's why we're going to do it. You should be familiar with this type of a system. We're going to stick a stop in here. We're going to go and place another stop inside of here, and then we're going to go and place a start, and then another start, and then a seal in contact, and then we're going to go and take all of that. Oops, sorry, that's a bad line there. Going up to there. Back to a coil, and then that coil is going to go through a set of overloads and back out. You should recognize this as being a standard stop-start station that you would utilize to go and run a contactor for a motor. We've got two stops that are in series. We have got two starts that are in parallel. We've got a seal in contact and a set of normally closed. If you do not understand this drawing at this point, you got to go back. You got to make sure that you're going to be prepared for motor controls this year, because this is baby stuff, all right? We are going to go far more in depth than this. But this is the one that we're going to work with today. So let's explain these logic gates, and as we do so, I am going to go and start to go and put these things in. We're going to go and call this thing here ES1, emergency stop 1. We're going to call this thing ES2. We're going to call this one S1 for start 1. We're going to call this one S2 for start 2 over here. And we're going to refer back to these. Now, this is a complicated bit of wiring when you got to go in and out. I don't know if you remember doing contactors, and then you'd have a pipe that would go over here, another pipe that would go over here to another box. And you should have done these things where you're figuring out the number of wires inside of pipes and back and forth. And it gets pretty complicated. What we're going to do in our systems is we're going to go and have just a single hot line that we're going to take around. We're going to run it to each of these devices and back to our PLC, and we're going to program inside of that. Let's start by defining the components, then we'll define what we utilize these things for. The first one that we're going to take a look at is going to be what is referred to as an AND gate. It has got this symbol right over here, and the AND gate is going to need to have two highs to go and make it a high on the output. So this and this, we're going to use ones as highs, we're going to use zeros as lows. If I have a high and a high, I'm going to go and get a output. both A and B need to be high in order for me to get an output. What we do is we will go and develop a truth table off of that. Truth table just tells us the truth about how this thing would operate with different combinations. Over here, if I have got this low and this low, I'm going to have a low output, right? We have to have both A and B high for Y to be high. So if both are low, we're going to get a low. If either is low, this one, A or B is low, we're going to go and have a low output as well. The only time that we are going to go and have a high output is if my A and my B are both high at the same time. We will get a high output out. These are going to go and be only true or high on this output when we have got all of our inputs high. Now they do go through a zeros and ones representing voltage levels, and they talk about how it could be plus 5 volts to 0 volts, and we're just going to quickly blitz through all of that. They're talking about what we refer to as TTL levels, or transistor logic, where we've got 0 volts, we've got 5 volts. Basically, there's going to be levels. Anything that is 0.8 and below is going to be seen as being a low. Anything that sits at about 2.2 volts and above is going to be seen as being a high. And we do have a small little ambiguous area here where it's going to be no man's land. It could be read as either high or low, so we just keep our signals out of that. But what we'll do is running into one of these things is as long as we provide at least 2.2 volts, let's call that 4 volts. We have 4 volts on that one, and if we have got an additional, another 4 volts on this one, we are going to go and get 4 volts out over here. It does not add voltages together. It just means that it puts out the same level as what the other ones were. So this one over here is going to be defined off of this truth table. We also define it off of a Boolean expression that we are going to go and have. And the Boolean expression for this one is A and B equals Y. It's a form of math that doesn't seem like math. 1 times 1 is equal to 1, right? That doesn't seem like math later on once we get into some of our other components, but it allows us to create complex mathematical statements that we can then define down and make smaller. This is Boolean algebra, and Boolean algebra is something you're going to learn about in 4th year. So we're going to leave it right now with just defining these, and then we can Booleanize those once we get into 4th year to go and combine stuff down there. There is a statement for this one that any low gives a low. As long as there's any low inside of here, we're going to always get a low output out of them. All right, straightforward enough. Where do we use stops? Or where do we use AND gates? AND gates are our most common way that we are going to go and combine stops, because an AND gate acts very similar to a set of series switches. For me to go and get this lamp to light, I need to have closed switch A and switch B for me to go and get that to light. Now, if we are working inside a motor control, we do have some series components. Take a look at this. ES1 and ES2 are a series set of components, so we can go and use an AND gate to replicate that seriesing up. This will make sense a little bit later, okay? Just wait for it. Don't get too impatient. We will explain what all of that means later. Let's talk about the next one down, which is going to be my OR gate. An OR gate is going to go and operate when either switch A or switch B is going to go and close. And I can think about it as being similar to a parallel set of contacts over here. As long as any one of these is high, I'm going to be able to go and get a high output out of my lamp over here. Once again, this is my equivalent circuit. How that looks over here, if I've got a 0 or a 0, I'm going to get a 0 output. We see that on this line over here. Nothing is high, therefore we can't have any high. As long as any one of them is high, A is high, we'll get a high output. Or if B was high, we would get a high output. Or if both of them were high, we would once again get a high output out of here. It provides a way that using individual inputs, we can simulate parallel operation. Once again, let's go back up here, and if we take a look, we see that we do have parallel operation off of S1 and S2, which are normally open starting types of contacts. So where does my OR gate get a lot of use? It gets used to combine start signals. All right? You should have this stuff noted down. ORs, start signals. ANDs, stop signals. Two common places that we are going to go and utilize those. Boolean expression for this one is going to be a plus sign that we are going to go and see. So, for this one over here, which is my OR gate is going to be A plus B equals Y. So 1 plus 0 equals 1, or 0 plus 1 equals 1. The one that gets a little bit trippy is if both were high, 1 plus 1 equals 1. In Boolean algebra, we can never go higher than the value that we started with. So 1 plus 1 equals 1. In other words, a high plus a high equals a high that we would have out of this. We define this one as off the statement, any high gives a high. The next one that we have is going to be our NOT gates, also known as an inverter. Couple of things I want to go and lay out. First of all, see that little dot? You need to know about that little dot. If you don't have that dot on there, you're going to be looking at a different type of electronic component, a buffer in most cases. If we see this dot, it is usually indicative of the fact that we've got a NOT gate. The other thing that's really cool about it is if I see those bubbles on any other inputs or outputs on other logic gates, those represent the fact that there's a NOT gate either at that output or at that input. All that a NOT or an inverter does is it changes the state. If right now the switch is in a 0 position, the lamp would be high, it would be on. If the lamp would become high, if the switch would become high, the lamp would become off, or 0 at that point. It's simply just going to be an inverter. Changes ones to zeros and zeros into 1. What we do for this is we just define it as A equals not A. Anytime we get a bar over top, this does not mean repeats into infinity the way it does inside of regular math. In Boolean algebra, it means is not. So whatever A was, A now is not going to go and be. Okay. You ready? Watch that bubble. What do we have over here? Over here we have got the NAND gate. Note that the NAND gate is composed of an N and the AND over there. It's an AND gate that is going to go and be inverted on my output. It's the same thing as if I have got an AND gate in line with a inverter. So what we're going to see off of this table is we're going to see the exact opposite of an AND gate. If we would go back to our AND gate right over here, my AND gate, we see that we have a 0, 0, 0, 1 over there. This one over here, this one over here, we see that we have got a 1, 1, 1, 0. Okay, I'm just going to draw the AND gate ones over here, 0, 0, 0, 1. That was my AND that I had over there, and I see that this is just an inversion of that. So what I can do mentally is I can treat my inputs as if they were an AND. A 0 and a 0 equals a 0, but then invert it through this, so that 0 becomes a 1. A 1 and a 0 is equal to 0, but invert it, that becomes a 1. A 0 and a 1 is equal to 0, but invert it, and that becomes a 1. A 1 and a 1 is equal to 1, but invert that, and it drops back down to a 0 over here. This one is defined off of the fact that any low gives a high. Remember that for my AND gate, any low gives a low was my statement. Now for my NAND gate, any low gives a high. We use the same beginning of that sentence, we just flip the output, the same as we're flipping the actual output. This one is less commonly used. We do have places where we can use a NAND, and I could use a NAND in what we're going to come up against here in a little bit, but it's easier if we don't. So we're going to leave that one alone. However, there are places where you can simplify by using these NAND gates. As far as the Boolean algebra over here, we see a bar over top of two of these together. Now note that that's a continuous bar going over top of both the A and the B. A and B, that little section underneath the bar, you should recognize that as being the symbol for and. And then if I take a look at the bar over top of that, that just means that I've inverted the entire thing, which is the same as me throwing that bubble on the back end over here and creating that NAND. We get another similar one, which is going to be my NOR gate. My NOR gate is going to have the same symbol as an OR gate, but with the bubble on the back end, right? We got that curved front. That's our OR gate. We got this bubble on the back end now, which tells us it's a NOR gate. It's the same as if I've got an OR gate, and then I flip the output itself. If I take a look at the Boolean expression, it's my OR expression, A plus B, but then it is knotted, or it's inverted on my output by me placing that bar over top of it. I don't know if you remember what the expression was for an OR gate. It was that any high gives a high. In this case, now that we're at a NOR gate, we are going to go and flip that expression around, and we're going to say that any high gives a low now. In other words, if I take a look at my inputs over here, this is going to be any high, or these is high. I'm going to go and get lows out of this over here. I do want to note that for my OR gate, this is also going to be the opposite of what an OR gate would be. A NOR gate gives us 1 and then zeros through all the rest of those. The OR gate gives us a 0 and then a 1, 1, 1. Like that is my output. Okay? It's just an inversion of that previous gate. Once again, the reason for this is actually that NAND and NOR gates are easier to create than AND and NOR gates. So they're more of a base type of gate. So we'll use them. And in some cases, just the Boolean algebra makes more sense to go and utilize these. Really, because NAND and NOR gates are the easier to create, for me to create and use AND or OR gates, these two over here, results in a greater propagation delay. Propagation delay is just simply the amount of time it takes for a signal to come in and change state and then exit as another signal. It's always going to take a little bit of time, so the more complex something gets, the greater that propagation delay is going to go and be. We are not going to go and use the NAND or the NOR gate when we are dealing with what we're going to cover here in a little bit. All right, we're just going to go and use those or know about them for now, and we'll deal with them later on as we need to. All right, we've got another really complicated one over here. This one is the XOR, and this one's got a weird symbol that's got a separated smiley face or Pac-Man face or whatever you want to call that. It looks similar to an OR gate, but it is going to go and have two lines coming into that. And what it does is it has a really, really special type of output. Basically, it only likes complementary inputs. Complementary means they are opposite and different. Zeros and ones or ones and zeros. What it does not like is it does not like to see two of the same. 2 zeros or 2 ones. Both of those just doesn't have much of a stomach for it. Just does not want to see them, so it's going to output a 0. Or it's going to go and output a 0 over here anytime that we've got similar ones. The only time that we end up with a high output is when we've got complementary inputs over here. Where do we utilize these? These are used for interlocks on a lot of systems. We've got a bunch of systems you would have covered back in level 2 under motor control. Yes, that's where we're going with this. You would have covered 4 reversing motor contactors. Should we ever operate a forward contactor at the same time as a reverse contactor? Absolutely not. It should only ever be operational in forward or in reverse. This is where something like this comes into play because we can use it to interlock. Right? This thing, I can use it to seal out some of my control circuit so that anytime that both are called for it to be off, it would turn off my contactors. Or anytime that there's a fault, an invalid inputs where somebody's calling for it to be in forward and reverse at the same time, it's going to lock it out. It's going to say, we're going to output a low right now because this should never happen. We can't operate in both at the same time. The only time that it would give us good, usable outputs would be when they're going to be complementary. Ones and zeros. All right? That's our XOR. Now we do have Boolean expressions that look a little different for it. 2 separate Boolean expressions for it. One is going to be a AB plus AB, and they're going to be knotted. So let me just draw those out over here. Plus A, B not. So not A and B or A and not B is equal to y, and you'd be able to do that off of this truth table if you want. You could go and take these, and multiply them together. You'll find that you're always going to end up at a 0 over here. That's one way that we can go and write it. The other one that we can go and write for this one is just going to be a specialized symbol that's got a plus in the middle of a circle. A, B equals Y. Once again, this is stuff that we are going to have to deal with later on when we get into Boolean algebra inside of year 4. We're not there yet. You are going to be there next year, so don't throw out these binders yet. You'll have to probably refer back to these. You'll see this one far more common than you'll see this. This is just a simplified version, but when you're doing Boolean algebra, you are going to want to use that one over there. All right, let's talk about the rectangular logic symbols. Rectangular logic symbols over here are going to be my European standards. European standards are definitely starting to show up in more and more places. Symbolically, they're not that different. Pretty much anywhere that I see a bubble on a NOT gate, a NAND gate, a NOR gate, I see a small triangle over here. Represents that same symbol that we would have over there. The rest is all going to be off of the symbol that is going to be inside of this. You'll note that for the AND gate, we've got the ampersand. That's what that fancy little AND symbol is called. So we have an AND inside of there. You'll note that for the NAND gate, it is the ampersand for an AND gate with that bubble on the back end, that NOT. Same as what this one is. It's an AND gate with a bubble on the back. This thing does the exact same thing. If I take a look at an OR gate is the greater or equal to 1. Anytime I've got an input that is greater or equal to 1, I'm going to go and get a 1 on the output, or a high on the output. Or anytime I've got a input, any high is going to go and give me a high over here. So this becomes my OR symbol. We'll note that for my NOR, I've got the OR symbol with the bubble on the back end. OR symbol with the bubble on the back end for my NOR. For my inverter, or my NOT gate up top over here, they just show a 1. That this thing is just going to not become whatever the status is coming into that. If it's a 1, it's going to become not 1. It's going to become 0, etc. There is one that is not shown on here. That is going to be your XOR. Your XOR gate is going to go and have the A, it's going to have the B, and it's going to go and have a symbol that is going to say equals 1, and that's going to be its output that it's going to go and have. So that's the only one that's not shown on here. If you wanted a XNOR, which is a XOR gate, that's going to be inverted. We haven't talked about them this year, but we'll cover them a little bit next year. That's just going to be done by adding that little inversion onto it. But we'll leave that one off there for now. This is my exclusive OR type of gate. Just recognize them. That's all that we need to be able to do. Okay, timing diagrams. Then let's get into some usefulness out of this thing. Timing diagrams are going to become a huge part of motor control. Timing diagrams are going to allow us to reference when something happens, and then we're able to go and infer from that data what exactly our output should be. Or from sometimes just looking at the data like that, we would be able to go and determine what type of a component would be making that. Let's take a look at a timing diagram. Timing diagrams follow a couple of rules. First of all, they are always read from left to right. Secondly, they are vertically orientated, meaning that any time that I'm looking from the top to the bottom, all of this is happening at the same time. So over here, we see we've got two distinct levels, high and a low. High and a low, high and a low on every single one of these. What we're seeing is that as long as both my A is high and my B is high, my output is high. However, as soon as my B goes low over there, my output goes back to low. Over here, I see that I've got two lows. Therefore, my output is going to be a low. Over here, I see I've got a low and a high, which is still going to be a low output. Over here, I've got two lows. When we move on to this, we see that we've got a 1 and a 1, and that we're getting a 1 out. When we've got a 1 and a 0, we get a 0 out. When we get a 1 and a 1 out, we see we get a 1 back out again. So this just allows us to go and get outputs and refer them back to inputs. Where this becomes really handy for us and where we're going to see it a load later on inside of motor controls is if I'm looking at an output line, let's say this over here is an output line, I can go and define what turns this output line on. It's usually the way that we read them is we read them backwards, not from following the inputs, but we look at the outputs and say what caused this to go and happen. And so in this case, if I'm trying to say what's turned Y on, I could follow that through and I can say, what turns Y on in this case is when A and B are both high at the same time. Check that over here. Yep, same thing that's turned it on. Check that over here. Yep, same thing over here that's going to turn that on. In both cases, A and B high is going to go and give me a high Y output. A NOR gate, well, we can go and take a look at the same thing. Let's go and follow through what gives our output Y. Over here, I see that I'm getting highs at these two states. And these two states are both low, 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 low over here. So anytime that everything is low, I'm getting this thing that is going to go and be high on the output. Or if I go through in the opposite way, I can read that over here is a high, over here is a high. I'm just going to label all these as ones. And I can see that over here, anytime that I've got a high, my output is going to be low. Anytime that I've got a high or a high, my output is going to go and be low. Anytime that I've got a high or a high, that's high all the way from there, my output is going to go and be low. So usually we end up reading these things from the output backwards. We will do some development of these later on. Okay, so now let's do something with all of these logic gates. We're going to do a little bit of function block drawing over here. You remember at the very beginning we said that what we want to do is we want to go and create a system that's going to look like this. Now here's where this becomes really useful. If I can go and take it, I'm going to draw that PLC thing that we talked about before. Can I move that? Oh yeah, perfect. Let's move that down there. Get rid of that. I don't know if I can move that thing any further. Right there. Good. That one there as well. Okay, so we're going to start drawing up top over here. Now I'm going to draw the circuit. I'm not going to go through the development of it, but we're going to go through an analysis of it. And what's going to happen is basically for my wiring, I'm going to go and have 4 input points. And I'm going to go and take in some start signals. I'm going to go and take in some stop signals. So right over here, we're going to start by taking in my 2 stop signals. Here, we're going to take in my 2 start signals. Okay, that's a start signal, that's a start signal, that's a stop signal, that's a stop signal over there. These are all going to come into my PLC. We're just going to draw this line here just to separate where the field wiring is going to my actual component. This is the beauty of programmable logic controls and digital controls in general, is the fact that instead of me having to have all that interconnection of lines going back and forth, all that I need to do is take a plus, we'll take 5 volts in this case, run that plus 5 volts out, and then I'm able to go and just grab a direct plus 5 volts off into every single component over here. It's fantastic. Quite honestly, it is. Because my wiring is super simple. Do I have a device? Run a hotline out to it, run a signal line from it back to my PLC. We're going to go and label these ones here. This is going to be my ES1. ES2, this is going to be my S1, this is going to be my S2 over here. And what we're trying to do is we are trying to go and control this contactor over here. So I'm going to draw that on the other side of the PLC. Now, what's happening inside of here, there's a bunch of other stuff where we have to address and set stuff up, but it's not that big of a deal. What happens is ultimately we're going to go and take this out to this component over here. Okay, this is going to be my coil, and then downstream of that, we're going to go and place these over there. So we're just going to go and create all of this in between. Is this easy for us to go and troubleshoot? Absolutely. If there's power here, the coil should be on. If there's power here and the coil's not on, the only thing it would be my overload. So it makes, for some really simplified troubleshooting. I'm going to go and draw out my gates in here. I'm just going to identify them as we draw them through. The first one that I'm going to go and draw out is just going to be an AND gate. That AND gate is going to go out to here. That AND gate is then also going to go out to another AND gate. Remember how I said that we take our stop signals and we combine them through an AND gate? Like that. That's what we're going to do over here. We're going to take that AND gate and we are going to go and run that down into that AND gate over there. This is done inside of a program. We use, drag and click boxes. It's called function block programming. It gets really intuitive later on. These ones over here, I'm going to go and run in through an OR gate. Remember how I said that anytime that we've got stuff that's in parallel, we run it in through an OR gate. Okay? Going back to this over here, stop signals come in series. An AND gate replicates seriesness. We run them through an AND gate. Start signals run in parallel, therefore we use them with our OR gate. So going back to this over here, we've got those two sets of signal that are going to be in there. This is now going to go into what we refer to as a feedback loop. And that might get a little bit tricky for some of you because you've never dealt with these things before. But your third years, you can handle it. I'll just finish drawing that. Like that. Then we're going to place that into there. And we are going to go and take this and we're going to run that into there. And then I'm going to go and run what's called feedback. Ooh, I know this is kind of trippy. Over here, back out to that point. Okay, so now we've got two OR gates. We have got two AND gates inside of here. And that's it at this point. Let's go and define whether stuff is going to be high or low at this point. Over here, taking a look at this, I see that this is going to be positive 5 volts, therefore it's going to be a high. So I've got a high over there. This one here is closed, it's going to be a high over here. This one's a open switch, so it's going to be a low. This one's an open switch, so it's going to be a low as well. Then we have over there, let me just put that one a little bit better. If I've got two lows on an OR gate, my output is still going to be low as well. Remember, one of them would have to be high for us to go and get a high through. If I've got two highs on here, this is going to be high as well. So we're going to run that as a high down to this AND gate over here. Now we're going to start with our system off. Okay, to be honest, I'm not going to go through the very first time we apply power to the system because it goes through a little bit of setup and contact race. We're going to say that right now the system is off. If this is off, that means there's a 0 being fed through into here, and that there's another 0 feeding from there into there, which means that this output would also have to be 0. And what we see then is that a 0 on an AND gate makes our output 0, and so it holds this. We basically formed what is referred to as a flip-flop or a latch or a memory state, all sorts of different terms that we can go and utilize for it. Let's watch what happens now as we run through it. So our output is off right now. If I were to press any one of my buttons down, let's say that I press this button over here down, this S1. What would happen is that S1, and I'll draw that one now in green, just to show that it's being changed right now. S1 would then change to becoming a high. So this is now going to become high. As soon as we get a high into an OR gate, the output goes high, which we then feed through into here. This output goes, our input goes high, which means that this output goes high as well. And over here now we have got two highs into an AND gate, which means that my output goes high. This is going to go and energize my coil over here. And I'm also going to have this one, this high, that is going to get fed back up and into here. Okay, I'm going to take my finger back off this button because it's a stop-start station, right? As soon as I take my finger off the button, this thing is going to pop back up. This is going to go back to a value of 0. So we're just going to go in, which would mean that this goes back to a value of 0 over here, which means that this goes back to a value of 0 over here, but we've already turned it on, so we're getting this feedback through here that's going to keep this thing on and running. So my system is now going to be sitting and idling along like this with my output running over here. What we then do is we can go and hit this stop, any one of these stops. I don't care which one, we're going to hit this bottom one over here. If I hit that stop, it's going to open it up, which means that this is going to become low over there. As soon as I get a 1 and a 0, this becomes 0. That becomes low. As soon as I get that, that becomes a 0. That carries over to there, which means that this AND gate is going to go and become 0. It's going to shut off. Shuts off this output. That 0 feeds back up and into here. 0, which means that this OR gate, it's got 2 zeros off of it, is also going to be 0, which means that we're back to 0 inside of here. So now we get this self-feeding, this memory state that's going to go and happen. I've switched that thing off. As soon as I take my finger back off this button, this is going to go back up to here. This over here would then go and close once again. This over here would go back to high. This would go back to high over here, but we see that our AND gate is still going to be blocking that thing off. And we can do any of these operations as many times as we want. You know, you hit the start button, you're always going to go and turn this thing on. You hit the stop button, you're going to go and turn it off. This is where you're going to find applicability of all of these ANDs and ORs and NOTs and NANDs and NORs and XORs is going to be inside of programming. Okay? There is, under programmable logic controllers, there's a couple of main branches of programming. We have got our ladder logic, which is really old. It's really easy for us to go and read and understand. It's really hard to write, but it's still in a lot of older installations. These days, despite what anybody that you work with might try and tell you about the value of ladder logic is dying. Okay, I was just talking with somebody from ABB, they're a major manufacturer, the other day, about languages, and I talked about a month ago with somebody from Schneider as well, because these are areas of interest that we stay up to date on. At this point, function block is probably sitting about 70% of the programming that goes into new installations is going to be function block using ANDs and ORs. Ladder logic, rapidly losing ground. The other one that's up and coming is structured text, which is going to be the Boolean algebra. You literally write stuff out using the words AND and OR, or using the plus or the multiply to go and tie them together. So that's where all of this stuff comes from and where all this stuff is going. That's the whole point of this whole logic gate operations, is that we use it inside of equipment to go and create operation. We will not build, at this point, we will not build stuff out of our LS7400 family of chips. It's just not worth the time and money when we can go and buy, you know, so many micro-controlled industrial processors, PLCs, for so cheap. In fourth year, you will still cover a little bit about integrated circuits. Don't worry too much about it even when you get there. It's covered there as a base of knowledge, but it's not something you're probably going to have to go and deal with a lot in the field. All right, that's it for our A6 line.